CG is going to do a presentation on that. Okay. So again, you can do quite a bit with geometry. And so the thought is that somewhere between 500 BCE to 300 BCE, this is about when Euclid's Elements was supposed to have been out. And Euclid's Elements is, so let's say the Elements are to ancient Greece as a big fat calculus book is to today. So just as that has the basics of undergraduate knowledge, at least in analysis, so did the Elements. It wasn't research mathematics any more than a calculus text is, but it was the elements of mathematics. It's what they needed. Okay. If you have comments or anything, I'll keep checking, have my eye over to the chat. If you have questions, you just post them or say them. Okay. Okay. So somewhere in this time period, we went from all is number to geometrical magnitudes. And again, since the Greeks wrote on paper, so much is lost. Like I mentioned that Euclid's Elements is written in 300 BCE, thereabouts. I think, yeah, I have to look at what I just wrote or what I just posted, but I think it's about 800. So a millennia later, that's our first copy that we have. So that's the first copy that still is around. Extant means it's still here. And this was based on something from 400 Common Era. So we're talking again, 700-800 years after Euclid. So we don't really know what was in Euclid. Our knowledge comes from this thing that we have that's 1,000 years, written 1,000 years after the fact. So when I say we don't know exactly what happened in here, it's the truth. And people have made arguments. Again, that's not what this class is about. I just want to give you a general idea. But, people have speculated about what happens here. But again, that's not my expertise, and that's not where I'm going to go. So what I want to do is I want to trace what it means to be geometrical. And I also want to trace how we get from Pythagoras to Euclid. And so those are the two things I want to do today. Okay, so questions? And I probably should have just made a video of this, but I decided to do it differently. Okay. Okay. So if you look at Euclid, and this is something one of the groups will talk about, is that it's based on using a ruler and a compass. That's it. So that's not the entirety of Euclid, but certainly book one. Okay. And a ruler is no measuring. It's just a straight edge. So you can't measure out an inch. And this is called a collapsible compass. I don't have a compass with me, but you've probably seen compasses, and you have a fixed leg here, and you have an arm that comes out, and then it'll stay where you put it, and then you can, trace a circle. Well, the ones that the Greeks imagined, it didn't do that. If the minute you let go, it falls back. So it collapses. And the reason that is so you can't copy things. You can't take a circle, measure it with the compass, and then make another circle. That's not allowed. Okay. There's other ways to do the measurement, but not by that. Okay. And so that's all. And so basically it's what objects can you create with just a ruler and compass? And the answer is quite a lot. So we don't know how this came to be, why these two tools, except that they're very common. And also because you can get a lot of things out of these. You know, you can prove the Pythagorean theorem, which you thought was about numbers. You can prove, you know, all the things from high school geometry, side, 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 etc. So side, 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 side angle, side. Okay, you can prove all those things. So you can prove quite a bit. And so one thought is that there was an existing body of geometrical work, and they just sort of amped it up and incorporated it. And again, these things evolve. They don't just happen, like people don't decide. Just as the Babylonians didn't decide to use base 60, you know, it just sort of evolved. You know, my feeling is that that's what happened here. So, okay. So again, so between 500, we went from Allah's number to Euclid and ruler and compass. And there's also a geometrical mode of arguing. And that's hard to describe. I should have had a sample for you, probably from Euclid ready, and maybe we can go through one next week. But it's a particular way of arguing. You're not using numbers, you're using logic, and you're using sort of, the question is, once you create something from a ruler and compass, that becomes a theorem. And so it's use the ruler and the compass to create theorems. And then the theorems you can use in geometrical arguments. That's one way to think about it. Okay. So I want to talk too, so I want to sort of examine this flow of thought. And again, I'm doing this from memory, so I might be wrong. So this is about 560 to 500 where he lived. Euclid is somewhere, I don't know, 428 to 448. I can't remember exactly. Sorry, that doesn't make any sense. 428 to maybe 348. I'm close if that's not correct. Aristotle was about 380 to about 323. Euclid, we really don't know much about. He's a man of mystery. He's not mentioned very much at all, but that's thought to be, I saw one source that gave that as his dates. So there's no overlap here, but there's definitely overlap here, and there may be overlap here. I want to draw that line too. Okay, so Pythagoras argued with structure. I'm not going to say rigor because we don't know, but he argued with structure. And he thought that math informed creation, that it was very closely related to the nature of things. Okay. Now Plato, he used one of the things he thought that arguing as a mathematician does is really good. It's very logical. So for him, mathematics was a model of argument, or rhetoric, let's say. He also thought that mathematical truth had its own existence. And something he called the ideal realm. Oh, I'm sorry. I just saw that from Daniel Madison. Okay, go ahead, Daniel.
Yeah, so this is a little bit off topic.
Sorry.
But how did people talk about math back then? Because I know like nowadays we have big conferences and we published papers, but did they, and like, especially from different societies, like how did they share ideas and stuff like that?
Okay. Remind me in a few minutes if I forget. I'm going to come back to that.
Okay.
Okay, and it has to do with these people, and I'll talk a little, but that's a good question. So mathematical, he thought it had its own sort of truth and existed sort of independent of humans. And there's this, I don't know, there's this, I can't remember if it's called the parable of the cave, and it's sort of these people live in a cave and all they see is shadows. Their whole life, there's a society that lives underground in a cave. And then they come out, finally somebody comes out and they see the sun. And instead of seeing shadows, they see the real thing. And that's his metaphor for our life. Our human existence is that cave, but there's this whole other thing out there where we really see things as they are. And so somewhere in that ideal realm is where mathematics resides. It has a truth. If we were to be wiped off the face of the earth, mathematical truths still exist. And that's a, and that's a whole philosophical debate I'm not going to get into. But that's probably a little bit of a caricature and a simplification of what Plato thought. But that's how important he thought mathematics was. And one of the things that he did was he had something called the method of analysis. And what you do is you assume, let's say you're trying to prove some proposition U for unknown. Okay, you want to prove U. So you assume U is true, and you start seeing you start following the implications. So if U is true, then so is P1. So, and then you find something else, P2, and then you keep going, and then you either want to find something you have that's false or that's true. So kind of there could be a bifurcation in either direction. Let's say the last thing we get is Pn, and then Pn is false. Let's look at that case right there. That would be like the square root of 2, because then we can reverse all these, hopefully reverse all these. Sorry, let me say that again. That because we assumed U and we ended up somewhere false, U had to be false. So the square root of 2 proof. Or you could do the same thing. You assume U and you assume a bunch of things, and finally you get to something that's true. Okay. So what this shows is that if U, then truth. But that doesn't mean U is true. If you remember that we can have a false, this can be false and this can still be true from Math 101. However, if you can reverse the arrows, and so we get what's true, that gives us Pn, that gives us the next thing in the chain, Pn minus 1. We go all the way back to P2. We can say that P1 follows, and finally we get to U. Then what we've shown is that U, if and only if, this true thing. And this would mean that U is true. So this is called the method of analysis. You start with something that you're trying to prove. One way to prove it is to follow its implications, root it in something true, and then see if you can reverse all the implications. Okay. Now that doesn't always work, but here's an example of where it works. I don't know, can anybody think of something that we do all the time where we assume it's true, then we get to something else which is true, and then we reverse all our steps? Can you think of anything that works that way? And then I'm going to pause after this to answer the questions from Daniel Madison and Viscara. Okay. Well, here's an example. When we solve this, we assume this is true. And we say, if this is true, well, if this is true, then 8 plus 7 is equal to 4x minus 3x. Well, if that's true, then 15 is equal to x. Okay, can we reverse these implications? So this was our u, this is P1, and this is going to be our true statement. Because you can make 15, you can let 15 be x. So we can reverse all these. If x is 15, then we can get, well, x is equal to 4x minus 3x, and 15 is equal to 8 plus 7. Then we can add 3x to each side and subtract 7 from each side. And we get 4x minus 7 equal 3x plus 8. So if this is true, then we can do that, and we can do that. And so we've shown that 3x plus 8 is equal to 4x minus 7 if and only if x is equal to 15. And we're allowed to say that. So that's an example of the method of analysis. And Plato's hope was that you could use that to discover things. You could use that to sort of speculate that something is true and maybe prove it. Okay, so this is Plato. And I think we said 420 to about 428 to about 348, something like that. And in 380, around there, he founded the Academy. Okay. Oh, shoot. Okay, good. I saw that somebody had some connection issues. So Plato's Academy. I'm answering Daniel Madison's question. It was a center of learning. Now, this is supposed to be the Mediterranean right here. Yeah, this is Gibraltar. This is what they call, like, Israel maybe is over here. Okay. And then Greece is in here, so maybe Greece is in here somewhere. Italy is over here. Here's Syracuse. Here's Alexandria. Okay. By this, but not by here. This is maybe a little too early. So circa 380. That there were Greek colonies all over the place. And so Greeks were always sailing to one place to another. And then after Alexander in 332, these were all Greek. So what happened is there was a center of learning at the Academy. People studied here. There was one, I'm pretty sure there was one in Sicily. That's where Archimedes was a lot later. So in the 200s, but thought to have been there before. Alexandria, there was this place called the Museum. So there were all these centers of learning. The Greeks were always trading, so there are always ships going back and forth. So one of the ways that knowledge was spread was people would write something down, and either somebody would carry it somewhere else, somebody would carry the knowledge, or people would travel and visit each other. So I imagine that it's similar to today. People would come to the Academy and they'd spread their knowledge, kind of as like a conference, or the Museum of Alexandria, the same thing. Okay, so Daniel, does that help?
Yeah.
Yeah. I am enjoying the thread about some entity that does not want Bryce to learn. Okay. Daniel Viscara, you said you had a question that was off topic?
Yes. Can you hear me? I'm having connection issue.
Yeah, I can hear you just fine.
So how would Pythagoras have visualized the proof himself? Because they have variables he could manipulate that easily in algebra and that kind of stuff, or was it more with pebbles that he would eventually come to these conclusions? Or how would he have gone about doing this?
We don't know. Okay, I mean, speculations are that you can discover things, you know, the way we might discover things with pencil and paper. They might have discovered things playing with those pebbles. When you read commentaries to individual things in Euclid, which, you know, 250 years later, are in Apollonius, which I haven't talked about yet, which was in the 200s, that there's these commentaries. This was thought to have gone back to the Pythagoreans. And so there was kind of a folk knowledge that some of these things that people were writing down in 300 actually had their formation back in Pythagoras' time. And so I guess the speculation is that they were trying to work out these notions of how to argue. So they probably would have used some sort of system of logic to prove things. But I imagine it could have been like today, where when you give a proof, except in 101, you draw pictures and then you try to convince the other person that it's true and use a mixture of like intuition and argument. That's kind of how I imagine it went, but we really don't know.
Okay, thanks.
Okay. Okay, does that help?
Yeah, it does.
Okay, good.
I mean, yeah.
It's not satisfying, but you know, the answer is, you know, the answer to everything is we don't know. But then we'll speculate and make something up that seems reasonable, but then you have to say you're making it up. But the fact that these things don't exist make it really hard to figure out. I mean, sorry, the fact that we don't have a paper trail of existing documents from that time make it really, really hard to figure out. Okay. And the arguments are ways that I've seen are very, very subtle arguments having to do with textual analysis and things like that. And it's not the kind of thing that I do. I don't study the antiquities, you know, which I think you'd really need to understand some of the, you know, to understand all the ins and outs of the arguments. Okay. Okay. So we have that, I drew that line from Pythagoras to Plato, and now I'm going to draw it to Aristotle. And that's an easy one because Aristotle, again, Plato, these dates are probably changing. Let's say 428 to 328. I think Aristotle was something like 384 to 323. That one I'm pretty sure about. Is that Aristotle was a student, like he was a brilliant student that walked in somehow. Plato got to know him, and he was like the star student. And so I don't know when he came to the academy, but he left the academy, according to what I've read, after Plato died, so around 348 with Plato's death. The academy is still going. In fact, the academy, or versions of it, closed the doors somewhere in the 400s of the Common Era. So it lasted hundreds and hundreds of years. So he left the academy in 348 and he started what's called the Lyceum. And again, that's another name. We have the academy, we have museum, we have a Lyceum. Those are all names today for centers of learning. So he started his own school also in Athens. And that's where the academy was. I did not mention that. Okay. And so he studied maybe not as much mathematics as Plato, but he further studied the rules of argument. Sorry, I think I'm frozen, so I'm going to wait until I unfreeze. Okay. 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 Hi, everybody. Are you able to hear me?
Yeah.
Okay, I'm back. Okay. I cut out for a while. I don't know if that was evident on your end, but my screen crashed. Okay. Maybe I got whatever Price has. Okay. Okay. So then I was talking about the rules of argument that Aristotle, it's one of the things he did. And he also talked about infinity, and I'm going to talk a little bit about that. And this was, the rules of argument that he studied were supposed to have a big influence on Euclid. Whether they did or not, we don't know. But he talked about having things like postulates, and you want as few as possible. And you'll see that Euclid had only 5 postulates. You'll see that on Tuesday, okay? And he also cataloged lots and lots of rules of argument. Okay. And so, for example, one rule of argument is this: all men die. Socrates is a man. Therefore, Socrates must die. Okay, so again, I think that's called modus ponens or something like that. I'm not quite sure. I can't remember. But he had structures of arguments. That were based, like apparently something like, 80 or 90, just different forms where one might argue a proposition. And so he named them all. Okay. And that's one of the things he did, is really carefully studied argument. He set up some rules about how to set up things axiomatically. So again, we see the thought coming from Pythagoras. It's starting to get really sort of this notion of using mathematical arguments. It starts to get refined here, and it gets really super refined by Aristotle. Okay. But I also want to talk a little bit about what he talked about with infinity. I'm looking at what Bryce said. It is spreading. So he believed in the potential infinity, or he articulated what he meant by that. And an example that, if you think about it, we extend a line in real life only as far as we need it. In real life, it's not infinite. But it can be extended as far as we need it. So this sort of infinite would be, in real life it's not infinite. But the fact that we can conceive of it as infinite, maybe up in Plato's ideal realm, that would be the absolute infinity. But the way we use it in real life, the practical way, we only use its potential to be infinite. And we still use that kind of argument. So let's prove that there is no largest number. So we're proving that the numbers are infinite. So we assume the numbers are finite. To prove this, therefore there's a largest number, m. Now, can I create a number larger than m? What do I have? What's the simplest thing I can do to m to get a larger whole number?
Just add 1 to it.
Yeah. No, but that's not possible, right? It's false. I can just add 1. Well, you say, well, that's the largest number. Now I can just add 1 to that. So there's no end to the numbers. But we really only, if you think about it, we never give an infinite set. We don't give infinite numbers. We're really relying on the fact that we can produce a number as big as we need to be. And that's, again, another example of the potential of infinity. The potential, not the potential of infinity, but potential infinity. And again, if you've used proofs limits, we usually use, we never use, we always use something finite. Let me give you an example of that. So we know that this series converges to 2. And then Sn is going to be the nth partial sum. So n is going to be some natural number. Okay. Now, the way that we do this to prove that the sum is equal to 2, we show that I can make Sn as close to 2 as I want. And you say, well, how do I do that? You give me a number a little bit less than 2. So let's say you give me some number d that's just slightly less than 2. So we have this relationship. D is less than 2. So what I do is I find an n such that this series, the finite series, is such that that is between whatever number d you gave me, which is really close to 2, and 2. And there's a formula that I can do this with. And the proof that this converge equals 2 is a variation of formalizing that process. Okay, I'm not going to go over it here, but again, we're only using, we never really add infinitely many terms. We only work with finitely many terms. Again, that's what Aristotle, I think, is talking about. Even though he didn't even conceive of these things, he's saying that we only use infinity in a practical way to the extent that we need it. We don't really use the infinity of that. Okay. Again, you could talk to Professor, it'd be interesting to have a conversation with Professor Porter about this, since he also has a PhD in philosophy. I think there are instances where you'd have numbers which are actually infinite. That's a whole different thing. But I'd be interested to hear his take on sort of some ways of mathematics where you're actually dealing with infinity. But when we deal with infinity in analysis, this is the way we deal with it. Okay, so that's the kind of thing that he was talking about. Okay, so we have that line from Pythagoras to Plato to Aristotle. And then we don't know this for a fact, but it sure looks like Euclid, how carefully he prepared the definitions and postulates, that he listened to Aristotle. He worked in Alexandria. I'm pretty sure we know that. Again, he was in Athens, and he was dead before Aristotle was here. He was also in Athens. Pythagoras was in Italy. So it could be that Euclid studied from people that studied at the academy, or he studied with people that studied under Aristotle. You know, he worked at the museum. Aristotle, again, worked at the Lyceum. Plato worked at the academy. So people are fairly convinced that there's connections there. We just don't know them. Okay, so I talked about ruler and compass math. And you'll see that that's what Euclid was all about. But there was also other kinds of math. You're going to see on Thursday something about the doubling of the cube. That can't be done with ruler and compass. We learned that in the 1800s, so a couple of hundred years ago. But still, people could study it. There's other problems called trisecting an angle. And that is taking an angle and finding the angle that this angle is 1/3 of that angle. So in other words, 3 copies of this angle make that angle. Again, that's not ruler and compass. That was also proved that you can't do that. And then you also have squaring the circle. And that is given a circle. Sorry, let me move it up again. Or so given, find a square such that that area is equal of that area. So again, that was also proven around the same time that you can't do it with ruler and compass. But people tried, and they also invented other kinds of math to look at these problems. And we'll see something about that from here on Thursday. And then we're going to get to Apollonius next week, and then Archimedes. And again, he did conic sections. Archimedes looked at spirals and then volumes. These were not ruler and compass, but they were still geometric. So they argued if you're an expert in Euclid, you would say, oh, this is the same kind of argument, just with different postulates and things like that. So again, even though the main stuff in Euclid was ruler and compass, not everything in Greek was, but it was still geometric. So Apollonius is, let's see, I think he's in the mid 200s. I forgot his dates. And then Archimedes goes from about somewhere around 280 to 212 or 213 or something. So these were right after Euclid, but they still argued geometrically. Now Archimedes, it was interesting what he did, because he also had a method, and we'll study this later, where he discovered theorems, and he used that to discover volumes and areas, much like calculus, very similar. And then, but he proved it with geometry. And we know this for a fact because of a really cool historical accident, which we'll find out about. So again, the point there is not everything was ruler and compass, but it was still geometric. But people like Archimedes actually maybe used other things that weren't geometric, but to discover facts, but then had to state it geometrically. And Newton did something similar. He discovered calculus in the late 1660s, and then his Principia Mathematica, which has a lot of physics in there, is geometric. So even he had a method, but he still chose to use geometry for his reasoning. Now it's not clear that Newton discovered calculus. It's very unlikely that Newton discovered calculus so he could do physics. But when he discovered calculus, we think for mathematical reasons. But when he discovered it, he no doubt knew its applicability in physics. But still, his big thing of physics was presented geometrically. So again, some of this reasoning of just using one kind of math, but then having to produce it in a different format, it's not just ancient Greek. We see evidences of that today. Not today, but in relatively modern mathematics. Okay. I got one more thing to talk about, but I'll pause for any questions. Okay, so I'm saying that Euclid really relied on Plato and Aristotle for the axiomatics. And I want to give you a really important example, but I am going to consult with the group that's working on the parallel postulate first. I don't want to steal their thunder. So our people that are working on the parallel postulate, I am going to talk about what happens when you negate the parallel postulate. But I don't want to do that if you're planning to do that. And I'm going to talk about the kind of geometries that come about. So I'm just waiting for your okay. If you say don't do this, I won't. So if you could just let me know, either speak out or send me in the chat, whether it's okay for me to talk about the parallel postulate and the kind of geometries that arise from its negation.
Yeah, you can talk about that.
Okay, good, okay.
I think because we're focusing more on the parallel postulate itself and the definitions, as well as the
Okay.
Playfair's axiom, equivalency, and all that.
Okay, good. Okay, so the fifth postulate, and I'm going to say something which isn't true precisely, and let the group that's talking about it correct me. If you have a point P and a line L, then there exists a unique line M through P parallel to L. So that would be the line M. And the way you'd figure it out is that anytime you dropped a line, a perpendicular from this line, it would be perpendicular to that line. Okay. And this is called the fifth parallel postulate. It's from book 1, and Euclid only had 5 postulates, and that it was an open question. Again, am I stealing your thunder here?
Nope, you're good to go.
Can you prove postulate 5 from postulates 1 to 4? Now, I say it's an open question because people tried until the 1800s to do that. And I mean the Common Era, so in 2200 years. And the idea was people thought, and there's some evidence that Euclid hoped this was true, that from the first 4 postulates, you can prove the 5th, and therefore you wouldn't need the 5th. And therefore, and you think about what Aristotle said about wanting there to be as few as postulates as possible, then that would sort of carry out that would be consistent with what Aristotle would love, even though he was dead before this, of having as few postulates as you need. Now, it turns out that the answer is no. You cannot do this. In fact, it's really weird. You can have a geometry, a ruler and compass geometry with postulates 1 plus 4, and you have the hyperbolic negation of 5. And what that says is that given P, not on L, where L's a line, there are more than one line through P parallel to L. So if here's P, here's L, we have more than one line. In fact, since you could stick any line, if this is like an envelope, you figure these two never touch this line. It's hard to visualize on a piece of paper, but then any line that's between these two lines would not touch this line. So you can actually, this is a valid geometry. And I'll show you a picture of it in a minute. Okay. So that's the hyperbolic negation. And then you have the elliptic negation. And that's that there's no line through P parallel to L. So that means if I take my point P and my line L, then any line through here eventually intersects here. Seems crazy. So there's no parallel lines. So that's elliptical. Hyperbolic, there's more than one, often infinite. And then Euclidean, so Euclid, elliptical, there's exactly one parallel. And all these can coexist with Euclid's other postulates. And so the fact that you can do that shows that none of these can be proven from the first four postulates. Okay. Anyway, so this is you study this in geometry, but I want to show you pictures of that. But it's kind of weird. So Euclidean, we're trained to think that way. That seems normal, at least to me. And these seem foreign. Okay. And so I'm going to share the screen, and this will be I think the last things that I have to do today. So I'm going to share with the readings section under Greece, and I'm going to look at the hyperbolic model. Are you able to see that? And if not, I'll just unshare and then I'll share again so you can. Can you see the picture?
Yep.
Okay. Okay. Good. Okay. So here's my point. Think of this as P. Sorry. Think of this as P. And this is L, this line here. And these lines, this is called the Poincare disk. And Poincare was a mathematician at the end of the 1800s. And so he developed a model for this kind of geometry by using a disk and by using curves, where curves are what's called geodesic. So the quickest path from here to here is along this line. And you can develop a mathematics that's computational that shows why that's true. So if we look at L, this is a line M right here. That's a line that's parallel to B. So is this line right here. So is this line over, no, that's not. But certainly these two lines, and then there's going to be lines in here too. And there's going to be other lines that can go through P. It'll be lines like this. Those are supposed to be arcs. And there's a way to make this really completely rigorous. But there's one example. But notice that the angles change. If we measure angles by tangents, you're going to see that these things have less than 180 degrees. So there's all kinds of funny stuff that goes on there. So this is the hyperbolic model. So let's put a big H for there. And again, if I take my P here, there's infinitely many lines through P that never touch L. And again, we're thinking of lines as being the quickest paths between 2 points. So doing something like this would take longer than going like this, or would be impossible. So can you think of a surface where the shortest distance between 2 points is an arc and not a straight line? How about the Earth? If I want to go from here, even to Omaha, but let's say from here over to Hong Kong, I'd fly along the surface of the Earth along what's called a great circle, a circle whose center is the center of the Earth. That's the quickest distance between Des Moines and Hong Kong, unless if I can tunnel through the center of the Earth, which I'm not allowed to do. It would take too long. It's not possible. So the Earth has these lines which are curves, so that, and I think of this as analogous to that. Like for some reason you can't go from here to here. You have to go along this path. Anyway, that's something you can talk about. This is hyperbolic geometry. It uses what's called differential geometry. So it's a whole nother subject. Okay. So I'm going to share something else. And I want to get rid of all my, okay. Are you back on the page? I don't know. I know where I am, but I can't tell if you see where I am.
We
I'm
can
on
see
the-
your web browser.
Yeah, and you see hyperbolic, elliptical, etc.
Yes.
Okay. Okay. So here's elliptic. Here's a model of that. And the straight lines are the lines through the North and South Pole, the great circles. So those are the latitudes, right? Longitudes, sorry, for long. Now, if I want to go from here, sorry, let me annotate better. Okay, annotate. Okay. If I want to go from here, sorry, let's do it here. From here up to here, I don't go straight, I actually go a curve because that's the quickest, that's a geodesic, that's the quickest thing. Now, so if I take this line and this line, let's say this is L and this is M, do L and M intersect? So is this true or false?
True.
Right, where do they meet?
North and south.
They meet twice. Okay. So we think of a line as a great circle. Let's just say the great circles that are longitudes. Oops, that should be poles. Are there parallel lines on the Earth? If the lines are equal to the longitudes, and again, that's the shortest path between 2 points, are there parallel lines? Or does every longitude intersect every other longitude? So again, does every longitude intersect, oh, I was wrong, they are latitudes. Does every latitude intersect every other latitude? So if I take this latitude here, does it intersect this latitude over here?
Yes.
Yeah, no parallel lines. And if we were to decide that we're going to draw our latitudes in a different direction, then the same thing. We just create new poles where they all meet. So there's no parallel lines on the Earth. That's an example of elliptical geometry. And so the irony is, people were really long in understanding that there could be these hyperbolic geometries, but we live on a surface where they're true. It's elliptical, where there are no parallel lines. But you have to understand that the Earth is cubed, I mean, is curved, but obviously we don't see it that way. We see it as flat. Well, depending on where you live. Here we see it as flat. Okay, does that make sense? So anyway, when the class on, just sort of to wrap things up, when the people present on the figurative math, that's going to be numbers like, rather than squares, on triangles and pentagons and hexagons. That's going to be Pythagorean, a Pythagorean concept of what figures are, that they're really made up of numbers. They're indistinguishable. Squares are numbers and they're geometrical objects, both together. So we're going to have another presentation on doubling the cube. You're going to see that grew out of a problem in the late 400s, early 300s, and its solution isn't by ruler and compass. That spurned a lot of really good, yes, you should invite the Flat Earth Society. So those kinds of things spawned a lot of good mathematics. You're going to see something on the parallel postulate, and even though you don't need what I just said to understand it, that's the context. That parallel postulate has just attracted attention for thousands of years because for a long, long time, it was an open question in Euclid, whether it was necessary or not. So when they go through talking about the parallel postulate, think of this as the full context of it. And then finally, you're going to see a proof of the infinitude of primes. It may be by algebra, but they're at least going to share with you Euclid's proof, and it's a geometric proof, which again, I find pretty fascinating. And we're also going to see a geometric proof of infinite series as well. Okay, so anyway, this is just to set the picture. Sorry to talk so long. I don't like to spend my whole class talking. It's not the most fun thing to see on Zoom. But on Tuesday, we will get into more traditional kinds of math and not so much talking. But here I wanted to sort of try to give you that sense of what happened between Pythagoras and Euclid. It's a long period of time and things really changed a lot. And I wanted to give you that sense. Okay, so questions or comments? Okay, that's all I have. So if you have, if the groups have questions, let me know. I can talk very briefly right now, but I can talk in more detail. I have a lot of freedom tomorrow and also on Thursday. So just let me know.
Have a good day.
Okay, you too. Thank you. Good luck with your computer.
Professor.
Bye.
All right. I'll see you, sir. I'm sorry.
Okay.
I guess so now. Bye-bye.
That was a funny line about the Flat Earth Society.
I mean, it was pretty interesting. I mean, I'm still surprised that people still have that society up.
Yeah, I know.
But yeah, I'll see you. I'll probably have a time, find a time for tomorrow or Thursday to talk about some the presentation thing.
That sounds good. Okay.
All right.
I'll see you later. Yeah, bye-bye.